I'm going to be talking about the ST Micro micro LiDAR sensors. These are the smaller and more inexpensive time of flight rangefinders that ST sells. And I just want to go over just the different generation slash families that ST offers, specifically with regards to using on a drone or a robot, and some of the downsides, some of the newer stuff that has caught my attention in the recent months. So the first one is going to be the VL53L1X. And they made an older version of this called the VL53L0X, and that one had a max range of about 2 meters. The VL53L1X has a max range of about 4 meters. In the API, or at least for the ultralight driver, you have to increase the timing budget and intermeasurement period to get anything close to 4 meters. I would say maybe a max of 3.8 if you're lucky with the right ambient light and surface reflectivity. You'd be lucky to get 3.8 most scenarios. And so this is one that I bought quite a few years ago. It's pretty low power. And then this one on the right of that is the Holybro version. It's 5 volt tolerant, whereas this smaller PCB is 3.3 volt power. To the right there is a VL53L5CX. It's a little bit newer. So this particular one is 3.3 volt. Again, you get the 4 meter ranging, but it's difficult to get even 3.8 or 3.9, depending on the surface reflectivity and your ambient light. You may not see that. You might see maybe close to 3.5. Again, you'd have to mess with the timing budget and intermeasurement periods to even get that long of a range. And then also the VL53L1X does have a short range mode up to 2 meters and then long range up to 4. I think most people are just going to use it up to 4 meters. The advantage with the 5CX is you get at least up to 60-degree field of view, whereas the L1X, you got maybe 27. I think there was a mode to get 15-degree field of view. And so, but the thing with these micro LiDARs you have to keep in mind is that when they say that the field of view, you have to implement it in the driver, in the application itself. It's not like a lightware LiDAR or some of the other more expensive LiDAR sensors where the field of view is already kind of taken into account with the sensor API. But the L5CX does offer that 60-degree field of view. That's what I'm using on my drone. I think I'm probably around 5 hertz is where I'm running the driver for this Pololu 5 volt tolerant L5CX. I think they sell them for around $20. It has a regulator on board, so you don't have to worry about a 3.3 volt dedicated rail breaking that out. You can just use this header, 5 volts ground, and then your SCL SDA for I2C. All these sensors are I2C. One thing I've noticed is in all of these ST Micro, these smaller time of flight sensors, you have to, once the driver initiates, you have to load the firmware. And so it's a lot of data that you have to upload from the microcontroller or the embedded board, the host platform basically. With the older L0 and L1X, you could get away with a microcontroller like an Arduino, 8-bit microcontroller, 32-bit. You're fine. With these newer sensors, L5CX and above, I noticed uploading the firmware just because of the chunks of data, the large chunks of data in the ultralight driver. It can fail on some microcontrollers that where you have to break down the chunks that even smaller than what the API has set. And even when I've done that on STM32s, I noticed the firmware upload does fail. So I'd recommend the legacy sensors using, you can use a microcontroller, you can also use embedded Linux as your host. With the newer L5CX and above, I recommend something like a Raspberry Pi, Jetson Nano, BeagleBone, Insert XYZ platform that's 32 or 64-bit ARM. So basically, you may be able to get away with the applications processor if it's powerful enough. I haven't tried it on one, but I would probably not spend the time and effort trying to get it to work on a microcontroller. I did spend a lot of time on that, many hours trying to get it to work on a 32-bit NXP microcontroller to no avail. I think I also tried on an STM32 based and also had issues with the firmware load again But I think ST markets the VL53 L7CX as a more of a successor to work better in higher ambient light scenarios like outdoors. I'm running everything indoors so far. And this is the Arc Jetson mounted to an EDU 450. I've got that L5CX mounted up front, working in collision prevention in PX4. And indoors it works really well. I'm not bumping into things that I'm facing, that I'm pitching forward into. It's actually stopping the drone, so that's good. Outdoors, I get a lot of really close false range readings, and I'm not able to get the drone to really fly at all. So I just turn it off when I go outdoors. And then indoors, I haven't tested in like a bright ambient light, but I would assume indoor lighting you probably find most of the way, unless you're like maybe light coming from a window might not work very well. Some outdoor light source that's stronger than like your indoor, even maybe an industrial light setting, it might be okay. I haven't tested, but for collision prevention, I think it's working well. One thing to note, PX4 collision prevention right now is not enabled by default with the acceleration multi-copter position mode. So I have to switch to smooth velocity and set jerk limits. So with the VL53 L5CX and even the older ones, you had this capability of grounding a pin that is like a reset. So you hold that to ground, and then you can change the other sensor I2C addresses on the I2C bus. That way you're not changing, you're not trying to change all of the sensors, or you get I2C multiple sensors with the same I2C address conflicts. So basically you want to reset all the sensors but one, and then change the I2C address of that one, then move on down the chain. In theory, I have the software that works for it. I just need to test it out. Get 4 sensors. So at 60 degrees, that's around 240 degrees coverage. You just do forward, backward, left, right, collision prevention. One of the other things with these sensors, I've seen people do like point cloud, like implement the point cloud library in ROS 2. I have a link to the repo. I have tested on the Jetson Nano. I have not tested on any other platform, though it probably may work on most embedded Linux. So that is the state of this project. And then I have to test the multiple sensor I2C address setting, and hopefully I'll have a better collision prevention capable drone.